All right, everybody, so we're back in the office after Computex, and this video is going to be a little bit different because during Computex, I actually interviewed Jakob Dellinger. Now, Jakob is a longtime personal friend and also a longtime friend of Hardware Canucks. And what he is this mastermind at Noctua. He knows everything, and he is willing to answer a bunch of questions. Now, normally we would have published this during Computex, but I wanted it to have its time to shine. So what follows is basically an interview, one-on-one, two passionate guys about air cooling, just talking about a couple of things that Noctua is coming out with. So basically the D15 and their upcoming 140mm fan and how those things mesh together, and how one, which is the fan, has been leading to the D15s or the next generation D15s delay over and over and over again. And to be clear, basically, Jakob said, ask me anything. Nothing is off limits. Nothing is forbidden here. This is all basically off the cuff, and they were willing to answer any of the questions that I put forward. So I hope that you guys enjoy this one. It's a little bit longer form content, but it is very, very interesting. Well, hello, everybody. This is going to be a little bit different one because there's so much technical details about Noctua's next generation, both D15 and the new 14 centimeter, 140mm fans that go into it. I needed a professional. So this is Jakob from Noctua. He's like their everything guy. He is their brains and the heart of the operation as far as we can see it. So anyways, I want you, Jakob, to go through all of the development that has gone into this, why it's taken so long, and where we are right now.
Yeah, with great pleasure. This fan has been shown at Computex multiple times. It's been on our roadmap for a while. People have been wondering what's been taking us so long to finally get it out. So we figured we'd take Computex this year as an opportunity to illustrate why it's so challenging to get this fan out.
So it's basically the grand reveal. We're finally seeing it, but tell me the process. Tell me exactly what went into it, because we've been talking about this for quite some time now.
Absolutely.
And it's been pushed back and pushed back and pushed back. And let's sort of like bypass the delays caused by the pandemic and just talk about the process that has gone in from almost like 2015 all the way to now in 2023.
First of all, the key challenge we're facing with this design is that we're improving on a fan, or actually two fans that are already highly optimized. First one is our current NFA 14, and the second one is the NFA 12X25, because it's a 12 centimeter fan, but it's actually a beast, especially on radiators when you pair it with our 140 to 120mm adapter. So this was the performance target we set out to bypass, and bypass by a meaningful amount. And this is basically what took us 5 years in the development phase.
So basically what you guys are doing is there's always that plateau of technology, right? It doesn't matter if it's smartphones or it doesn't matter if it's fans. It's like to break through that glass ceiling typically takes a lot, especially when it comes to something that's so highly optimized like fans, or even in this case, air coolers, because where do you go if not going to like an AIO and water cooling? So that's part of the whole process that goes into this, and it takes half a decade in some cases.
I would say it gets exponentially more difficult the further you push the optimization. And in this case, it actually resulted in a development phase where we had 4 points or 5 points where we had to go back and start from scratch, because the approach we took could just not be further optimized. So you should not think of a development process like a linear development where we just keep tuning one design until it's there. But in difficult cases like this one, it's more like several iterative feedback cycles where we work on an approach, tune it as far as possible by simulations, by prototyping, feeding the test data we get from the prototypes back into the simulations, further improving. But then we sometimes hit dead ends where we see, okay, this just cannot be pushed any further. We need to take a new approach.
So it's almost like instead of pressing the undo button, you basically have to press the delete button, start all the way from scratch, the process starts. And it's not like in this case, you're trying to sort of like add evolution to a fan. You're actually building up brand new.
Yes, absolutely. When you look at the impeller samples we have on display in the back here, you can see that these are like drastically different designs. They all follow different design approaches. that we took in order to get to that goal where we wanted to head in the end. In 4 of these cases, we actually were in the situation I just described before, that we realized that we just cannot optimize this further, and we had to start with a new approach.
And it's also a cost perspective too, right? Because this every single development represents money, lots and lots of money, lots of man hours. So that's something else to take into account.
Absolutely, that's the case in the development phase, but it's actually even worse in the tooling phase and the final validation phase we'll come to in a minute.
So after we went through almost 6 models, what made you choose the last model?
There's 2 key points. First, we need to meet the performance benchmarks. So we need to have a fan that performs as good as we want, and that means not just putting in another radiator saying, oh, it's better than the last one, but it's going through various different heat sinks, various different radiators, different cases, different case panel types like honeycomb, holes, slits, push, pull operation, make sure that there is no issue in any of the applications, and we see superior performance in all of them.
So
this is the first checkpoint we need to meet, and the second is that the fan can be produced in mass production.
Right.
So another dead end that we can have in the development process is the one you can see from 2016. It was actually performing pretty well, but it turned out that it would not be feasible in mass production.
So what you're trying to do here is optimize for an all-round fan. So we're not talking about a specific radiator fan, we're not talking about a specific airflow fan. This is really a balance of airflow and static pressure, plus the ability to mass produce it.
Absolutely, absolutely. We have the PQ curve on display here,
so explain what the PQ curve is to the folks at home.
Yeah. The PQ basically shows the key performance characteristics of the fans, because there's much more to fan performance than just the PQ curve. But typically people tend to look only at airflow pressure specs, but these are basically meaningless, because pressure specs are given at 0 airflow, so at the so-called point of no delivery. So this is not a realistic use case. This is the fan blowing against a flat wall, and maximum airflow specs are given at 0 pressure. That this is basically at the pressure differences at both sides of the fans evened out. So that's not artificially evened out. So that's not even free air. It's less than that. So exactly. Absolutely 0 resistance. Both of the applications are meaningless. What you want to know is what happens in between on this curve. And you can see the resistance curves that we've plotted here. Typical case resistance curve, relatively low flow resistance, heatsink, slightly higher resistance, radiator, even higher resistance. So what you want to know is what the fan does in the mid part of the curve.
Exactly. So what you're trying to do is optimize for the highest point within the middle part of the graph.
Yes.
So balancing your airflow and static pressure.
Yes, exactly. So for example, you could create a fan that had a curve like this. It would be very good at as a case fan, but it would do poorly on heatsinks and radiators.
Yes.
And that's not something you want to have. So this is one of the key challenges in the development phase.
Great. So now that we've gone through sort of like the development phase and all of these models, what was your benchmark target of improvement over your current generation fan?
The one we were finally happy with, we have a real world performance data up there. It shows roughly a 3-degree performance improvement on an average 140 millimeter radiator. So that this was what we were originally setting out for.
Yeah.
It actually overshot our benchmark a little bit. We thought that something like a 2.5 degree improvement is something that would be meaningful enough for customers to do an upgrade, and so we're super happy that in many cases we're actually closer to 3 degrees.
So it's almost like here, what we're seeing here is almost like an inverse torque curve on a car, right? Because the best torque or horsepower on a car would basically be a completely linear graph that went all the way through the RPM range, right? Whereas here, what we're seeing is a more robust improvement, a flattening of the line through that sort of like critical zone right in the middle where you want it for that balance of both.
Yes.
Yeah.
Excellent.
So now that we've understood the basics of where you wanted to sort of get to, where did we get to, and what is the technology that went into it?
I would say the key parts to this fan are first of all the super tight tip clearance. This is something you've already seen with the A12X25 where we use a 0.5 millimeter tip clearance. This one's going to have a 0.7 millimeter tip clearance, which sounds like it's easier to pull off, but sadly it isn't, because it's a 140 millimeter fan. So due to the larger diameter, you have more centrifugal forces acting at the tips of the blades, more rotating mass at the tips of the blades, and this makes it more challenging to manufacture with a 0.7 millimeter distance than with a 120 millimeter fan with a 0.5.
It's sort of like how a larger car tire and wheel is harder to balance than a smaller one. Yep. The larger you go up in radius, the more mass you have on the edges, that sort of knocks everything out of balance, right?
And once we will get to the final validation process later on, another key challenge with this tight tip clearance is with a 140 millimeter fan, any slight deviation in angle will have a larger effect at the tips of the blades due to the larger diameter. So this is what makes it so critical to build a 140 millimeter fan with such a tight clearance.
Right.
And I would say that the second key benefit, I don't think we should go through all of the points,
no.
But the second key point about this design and what also differs from the other approaches we took is what we call the progressive bend impeller. When you look at the fan blades, you can see that they actually bend progressively.
It's like a shark, almost like a shark tooth effect.
Exactly.
Yeah.
And the reason for this is that you have a drastically different aerodynamic situation near the hub of the frame versus the tip of the blades. Because the tips of the blades, especially with a 140 millimeter design, move very quickly versus the parts of the blades near the hub only move very slowly. So you get very low airflow performance near the hub, high performance near the tips. So what you want to do in fan design is to achieve as even blade loading as possible, so that the central part can still do part of the work, and you don't run into a situation where the part near the hub is so inefficient that in a high back pressure situation like on a radiator,
correct,
you would end up having airflow going back through the fan near the hub. And this is why the part near the hub has actually a different curvature and profile to achieve the desired performance despite the lower speed of movement.
Which totally makes sense, but I also see, and you guys are probably seeing right now on the B-roll, is that the actual center hub has small sort of like striations in it, whereas every other manufacturer that we've seen is basically a flat hub.
Yeah, we call this centrifugal turbulator design. The purpose of this is that we help to push air out towards the outer higher performance region of the fan blades, and at the same time create turbulence near the hub so that we can have better flow attachment on the parts of the blades near the hub.
So has anything been put into this fan to eliminate the dead zone on the flip side of the fan? So that's something that has come up quite a bit, because some of these the fan hubs are getting larger and larger and larger, thus technically increasing the dead zone on a radiator. What have you put into?
Honestly, I would say that this entire concept of a dead zone probably is a bit outdated from the years, maybe the early 2000s, when we had relatively small heat sinks.
Exactly.
Maybe even not having heat pipes that were hot in the center, and then you had a 60 millimeter fan or an 80 millimeter fan sitting on top, where you actually had a hot spot in the center. With the large fan designs we have today and the large surface radiators, this is, I would say, not that much of a thing. And you also have the problem that, as I've explained before, it's very tricky to get performance out of the fan near the hub anyway. Mm-hmm. So it's not like reducing the hub size and therefore reducing that so-called dead spot would automatically improve your performance. By contrast, you will end up with more blade regions that's actually low performing and a higher risk of airflow going back. So there's nothing done to address that as such, because I don't see it as an issue. What you could do to improve performance on radiators or reduce the zone behind the fan where there's little airflow hitting the radiator is adding basically they're designed as inlet spacers that we launched later this year, but they can also be put on the outlet side of the fan. So you're increasing the distance between the fan and the radiator, and therefore there would be slightly more even airflow hitting the radiator. But honestly, on the outlet side of the fan, the returns you get from this are
minimal.
really minimal, like barely measurable unless you have a very, very good setup to measure.
Got you. And the other thing that I've noticed is that there's been, at least from my perspective here, a little bit of a revision in your fan clips as well.
Yes, absolutely.
Can you go through that?
Yeah. I've already briefly touched on the issue we have with the tight clearance. There's multiple problems we've run into with due to that tight clearance. One is that, and this is one thing that caused the latest pushbacks on the roadmap, that we have discovered that it's honestly something we haven't seen before, because we've never been so much on the edge of what can be manufactured, that the mounting force of the fan clips actually causes a slight deformation of the fan after multiple years of usage under elevated temperatures.
Really?
It's illustrated here. When you have the fan clips pressing on top of the mounting points, the fan frame will
It's almost like it's
just
warping.
so slightly warp like this. The sides will go inwards, and if you have a clearance of 0.7 millimeters, and the fan will go, the frame will go more narrow by, let's say, 0.2. Over a few years of usage, you're already like super tight, and this is something we would just not feel comfortable with.
You need something so exacting in order to sort of like compensate for that small gap in there, basically.
Yeah, exactly. So the new fan clip design we've come up with no longer goes into the top mounting holes of the fans, but into the bottom mounting holes of the fan, and this way we put much less stress onto the fan frame. But there's actually a second thing we did to mitigate this issue, and this is what we're currently testing, that we are actually going to switch the frame material from ABS PBT to a liquid crystal polymer as well.
So
initially,
our plan, your Sterox.
Yes.
Yeah.
Initially, our plan was that, like with A12X25, we wanted to use Sterox for the impeller only, but not for the frame, simply because the cost is quite significant.
Yeah.
But the issue we saw with the fan clips and also with radiator mounting screws, which also apply pressure, especially if you tighten them hard, actually prompted us to now evaluate using LCP for the frame of the fan as well.
So the other thing that people will probably see is that there's two different types here. One of them is for a typical heatsink fan, and then your other one is your typical case fan.
Yes,
right?
absolutely.
So when are we going to actually...
And radiator fan.
Fan, of course. So when are we going to see these?
When?
When? It's sort of like, when is the next Half-Life coming out, right?
Yeah.
When do you guys want to see? You probably wanted to see it like 2 years ago.
Yeah. Same for me. I would love to have them on the market like 2 years ago,
exactly.
3 years ago. Let me walk you through two of the key steps of the validation we do for fans, because this explains why, if we see an issue, it pushes the fans so far back.
Okay.
So initially, we had further delays before, but a while ago the target was to release it end of next year. And then when we started mass production, our manufacturing verification test in the last stages revealed that we had a very slight issue with deviation from at the hub region and straightness of the axis. This is after like multiple years of usage at elevated temperatures, but still it meant that we fell below the specified clearance limit.
Sorry, we're talking about micrometers here.
We're talking about 1/10 of a millimeter difference.
Wow.
That let us go below the tolerance we need.
Got you.
And this manufacturing verification test is a test that runs for 4 months. And it not only runs for 4 months, it also takes weeks to prepare and weeks to analyze afterwards, because we need to put 50 fans into the test. And we basically need to do something like a full health check on each of the fans that goes into the test. This means performance check, acoustic check, electronic check, and most importantly, 3D scanning. And the same has to be done afterwards so that we can track any changes that occurred over those 4 months. So whenever we see an issue that prompts us to go back to a point in the development cycle before that MVT test, it means that we have to repeat that test. And repeating the test is not something you do in a day.
Months and months
it means like 6 months alone, usually, with the preparation and the analysis afterwards. And the issue I've described before with the pressure from the fan clips and the radiator screws is a similar thing, because this is something that's revealed in the long-term thermal creep test that also runs several months and takes similarly long to prepare and to analyze. And this is why we had such significant delays on the fan. And at the moment, we're targeting and hoping to solve the problems by switching to LCP for the frame, but the tests are running, and if we see any further problems in the test, it will set us back to a point in perhaps in the tooling phase where we actually need to rework the injection molding tool, need to retune the injection molding parameters, hopefully not create a new injection molding tool. But any of these issues occurring at such a late stage basically automatically mean a delay of half a year or more for us.
It's more than just a small speed bump. It's
yes.
like, look, perfection takes time, and this is how you achieve perfection or near perfection.
Yes. So what I can say is that if the tests that are currently running are going well, our target is to start mass production towards the end of the year and then have the fan on the market in Q1. What I can say is that so far everything looks good, but if there are any further issues, I cannot rule out that we have to delay the fan further. And I mean, the obvious question to ask is, why go for a design that's so much on the limit of what's possible manufacturing-wise anyway? Why not make that bloody clearance a little bit bigger, right? What I can tell you is that we did think of that.
But why not, I guess? That's always a question. Why not go sort of like to the next level where it's very hard for others to achieve the same thing? You know?
Yes, but why wouldn't you go for the easy option if the trade-off was minimal? But Correct. What I can tell you is that the trade-off isn't minimal. We experimented with increasing the tip clearance by 0.2 millimeter, which doesn't sound like much, but it resulted in a rough noise increase at free flow of around 2 dBA and a roughly 10% drop in flow rate through a radiator. Wow. So we're really talking about significant performance penalties here, and this is just something that we would not be willing to accept at Noctua. And as frustrating as it is for customers and for ourselves to have these delays, we think basically this is the only way to go, because we don't want to go out with a fan that is compromised on a performance level or compromised on a longevity level, which would be the other way to go, which would be to say, okay, we can accept a certain failure rate, or we can accept that the fans fail after, I don't know, 7 years of usage because we give 6 years warranty, but that's not something we want to have. We're always proud if people approach us who are running fans that are 10 or 15 years old, and we definitely want that to be the case with this fan as well.
Best support structures in the industry. So let's see how that all evolves now into the D15. So now that we know the fan, that's sort of like the heart of the D15, let's talk about the cooler itself. Okay, so I'm touching the new D15 finally after all of these years. So Jakob, just take me through what has changed, because from my understanding, this is more of like an evolutionary approach rather than a completely ground up new design. So tell me about what you've done to this to optimize it for current generation processors versus, you know, the old D15, which was for a very, very different generation of CPUs, and what has changed versus what we know now as a D15?
I would say the first key difference is that we're obviously going to make good use of the new fans we've developed. And the second part is that we've, of course, optimized the heatsink for these fans. So you always want to tailor your heatsink to the fans you're using. We've already talked about the improved pressure characteristics of the new fan, and these actually enabled us to tune the heatsink a lot. So the current generation D15 has a fin pitch of 1.9 millimeter. This one's going to have 1.6. And the actual overall dimensions are the same, actually slightly smaller, same height, same width, slightly shallower profile, 9mm shallower profile. But due to the tighter fin pitch, we could actually squeeze in 20% more surface area.
So basically that tighter fin pitch is due to the fact that you're able now to have a higher airflow, higher static pressure fan, basically pushing through.
Exactly. If we did that with the same fan, with the current A14 fan, we would see diminishing returns, or actually even slightly lower performance, because the resistance curve of the heatsink would be so high that it's actually too far up on the performance curve of the fan. So we would reach stall condition on the fan, which is something you never want to do, both for acoustic and performance reasons. So this is why it's so important to tailor a heatsink to your fan design. The second key difference to the current D15 is that we're now using 8 instead of 6 heat pipes. And the upside of all the delays we had with the fan was that we had way more time to optimize the heat sinks. What I intended to say was to optimize the heat pipes.
Okay.
Because heat pipes are seemingly simple, right? But you can tune so many of the parameters, like the wall thickness, like the pore size, the thickness of the wick structure, the fill rate, etc. And taking the time to optimize that for a specific heatsink is crucial to really make the most out of a particular heatsink design.
And what has anything changed with the contact plate itself? Because the way current generation CPUs are designed, everything from the size of the IHS to where the hot spots are in there, how concentrated that heat is, how is that sort of factored into the evolution of this?
The contact surface of the cooler is slightly larger than current D15 due to it having 8 heat pipes, and it would simply not be possible to fit 8 heat pipes on the current D15 base. However, even the current D15 base gives you full coverage on LGA 1700, which is currently, on the long axis, the largest IHS we see in the desktop space. So there's not that much difference in this regard, I would say. I would say the key optimization we will have included with this cooler for current processors is something we probably come to talk about in a minute, that this is our offset mounting for AM5, where we actually shift the cooler slightly towards the south side of the socket so that it sits centered over the CCDs of the Ryzen 7000.
Yeah, so we actually have a completely separate video for that coming right up. Once it's published, I'll leave a link right up here, but basically it goes over everything about this offset mounting kit. In addition to that, a direct die kit that they have coming out. The cool thing is that the offset mounting kit will be included with this cooler. So other than that, has anything else really changed with how you position everything from the heat pipes to the base? Anything else, or that is basically, this is an evolution that's really based on a fan revolution?
I would say that the fan revolution informs the tuning we did on the heatsink on several different levels. We already talked about the fin pitch. Another aspect that we could mention is the depth of the fin stack. So you can see that the front stack is slightly more shallow than the rear stack, because with the combined pressure of the two fans, we can actually push a little bit more air through the rear stack. So we could optimize performance a little bit by making the rear stack thicker than the front stack. Another design change that we could mention that is unrelated to the fan, though, is that it now features an offset design. You can see that it's slightly shifted towards one side, like you already know from NHD15S.
Correct.
So we get better PCIe clearance compared to NHD15.
So the other thing that I was also wondering here is, if there is any changes now in the design process of the fans, because you might, like you were saying, there might be a very large road bump in this whole production. Yeah. Would that impact in any way the D15 as well?
Certainly from a time frame perspective. So we already discussed about the new fan hopefully being ready for production towards the end of the year and then being on the market in Q1 next year. So our current target is to have the cooler follow by Q2 next year. Definitely, if we have to further delay the new fan, it would also impact the cooler, and
but it wouldn't really impact the design of the cooler itself, because you know what your fan specs would be.
Yes, this is like unless we're hitting a catastrophic
please don't, we want it now.
Results where we need to design a completely new fan from scratch.
Please don't.
And then let's meet again in 10 years from now. No. I can tell you how D15 C2 will look then, but I really don't hope that's going to be the case.
So, okay, the last question before we sort of like sign off here is, do you believe at this point in time, like this is the pinnacle right now of your fan design? If you could predict, so maybe like 5, 10 years down the road, in order to push through this plateau that we've reached again, the effort that you've put into this, can you see this almost as being that pinnacle at this point in time for 140 millimeters fan design? And I'm sure that you're sweating right now. I'm sure I saw a sweat break out on his head. He's like, imagine what it would mean for the company to do this all over again. But it's a challenge for engineers and technology, right?
I was starting to smile when you said that, because we do have our plans.
Oh, yeah.
And I do think that there are possibilities to further push the envelope. But I'm
That's
not
so
going to
exciting.
tell you
So exciting.
what's the approach going to be like. I do think that there's room for further improvement, but we're definitely talking about a similar time frame it took us for this one to go. So it's not something you're going to see on the market in the next 5 years.
So at this point in time, when the fans are ready, the cooler will be ready. So this is basically probably, look, we've seen a lot of things here at Computex. From a personal perspective, this is probably the most exciting. I know I nerded out a little bit in this video, but it was absolutely worth it. Jakob, thank you so much for your time.
My pleasure.
We've known each other now for like 15 years. Yes. I have to say congratulations on all this.
Thanks
I'm Mike with Hardware Canucks. This is Jakob with Noctua, and I will see you in the next one. And hopefully, next time you see him, we're going to be talking about even more new cool products. Take care, guys.
Thank you. Bye-bye.